technology forum that bring innovation earlier to the market and accelerate decarbonization.
Decarbonization is a mega trend which the semiconductor industry must ride on through bold ambition, greater innovation, and cross-sectorial partnerships or collaborations to thrive in a low-carbon future.
Decarbonization and digitalization are the two defining trends of the coming decades. They will profoundly change the world we live in and the markets we serve. Semiconductors are key to decarbonization and digitalization. They are needed more than ever to drive the transformational change we need for a sustainable future. At Infineon, we want to leverage the great potential of semiconductor technology for innovations that really make a difference.
And this is how the entire reliability map has been carried out in our lab. So the first aspect after failure identification, we say that the mission profile study has to give a very good coverage. That means what type of mission profile that my device can encounter. In automotive applications, your device under test can face severe profile due to the extreme behavior of the driver. The driver could be aggressive. The driver could have multiple scenarios that give your duty different driving cycles, and then your vehicle could have extreme payload. That means it is designed for maybe 1000 kilogram of payload, but sometimes it could carry more than twice, maybe 2000 or 3000 kilograms. So it is an example. Actually 1000 kilogram is nothing. It could be like 80 ton. If your vehicle is about to carry an 80 ton payload, but sometimes that user may give it more than twice, like 2 ton, like 180 tons of payloads. So that is also give and different behavior for your device under test. And then extreme weather. So your EV could run at Norway where it is minus 35 degrees centigrade, and again the same EV could run at Saudi Arabia where it is the ambient is around 45 to 55 degrees centigrade. So this extreme behavior could also taken into considerations when the lifetime study has been carried out before the product going to production line. Then this is a classic example. What could be the mission profile? So number one, the battery technology, whether it is a high power battery or high energy density battery, like whether it is NMC, LFP or LTO battery, and what is the initial SOC of the battery, whether it is 95% initial SOC or 90% or 80%. The initial SOC has different behavior or different stress on the DUT. Then speed profile. That means whether your EV will encounter an normal behavior like NADC, or whether it will encounter a very aggressive profile like WLTP, or it will be used in urban area, or it will be used in hilly track area. This speed profile have different stress on the device under test. And then also the charging characteristics. Like what are the characteristics that could trigger the fault, like whether your EV is subjected to fast charging, medium charging or slow charging, whether there will be preconditioning after charging or not, whether there will be preheating before charging or not. So this could also trigger fault conditions. Then also road characteristics, like what will be the usual traffic that the vehicle encounter, what will be the road slope, and the number of passengers that it could carry out in case of maximum number of passengers and minimum number of passengers. Finally, the environmental conditions like the temperature, wind velocity, these also have to taken into considerations when we are going to see the failures and also the lifetime of the device under test. That is basically a power electronics component. That means to identify the power electronics components lifetime, all these factors need to be taken into considerations for vehicle. And when the vehicle is modeled, the parameters has to be taken from OEM so that we have a very good idea about the weight, drag coefficient, power ratings, and the component maps. That means how much the components could carry out in terms of power level, energy level, and also in terms of lifetime. So once the mission profile studies has been done, we have to go deep actually. That means now we will go into the device level loading. That means the mission profile is the upper level of the subject. That means the mission profile is subject for the vehicles. Then we comes into the device level loading. That means what are the device level loading that is actually loaded your DUT, and in this case the DUT is power electronics converter. So again it is the battery voltage based on the technology, whether it is NMC, LFP or LTO. The battery voltage has been changed. That means if the battery voltage changed, your input voltage of the device under test is also changed. Then the load profile, actually the load profile means the power request to the component. Then the coolant profile, that means the ambient temperature that is going to be applied on your device under test. And finally the control strategy, that means the PWM control strategy, whether it is direct fog oriented control, whether it is indirect field oriented control, whether it is model predictive controls. Sorry, it is not direct fog, it is direct field oriented control. So based on the control strategy, the device under test could encounter different level of stress. So all this device level loading has impact on the thermal cycling and the lifetime of the DUT. Then we will give some classic example from our study. So here we see two profile. One is extra urban, one is urban. That means based on the mission profile, the speed, the load power, the coolant temperature is different. So here the speed in two different profile is different. The coolant profile is different, and also the battery voltage is different. So finally we see the electrothermal stress on the switch. That means the maximum junction temperature of the switch. In one case it is reach 100 degrees centigrade, in another case it reach around 130 degrees centigrade. So it is the same switch, the same DUT facing different mission profiles given different electrothermal stress on the switch. Then it is a classic example. So the vehicle at first encountered to the same profile, but it is encountering the same driving profile based on fast charging and slow charging. What does it mean? It means that DUT, the vehicle at first go to a charging stations, and it is subjected to fast charging and then driving US06 drive cycle. And in another case, it's subjected to slow charging and then it drives US06 drive cycle. In both cases, we see the coolant temperature reach 105 degrees centigrade after fast charging, because the fast charging takes the temperature almost 105 degrees centigrade, and in that case the DUT, when it is subjected to another driving cycle, it reach to the maximum of 145 degrees centigrade. In another case, after slow charging, the DUT barely reach 110 degrees centigrade. That means how your vehicle will be treated, whether it will face fast charging or slow charging. Based on that, the coolant temperature of the vehicle increase, and that has a severe impact on your inverter. So this is the output of the profile. That means you are driving after charging, so how you will do the charging, that also impact on your lifetime. Then this is another example. It is the same EV and same inverter facing the same WLTC cycle, but the control of the inverter is different. In one case it is model predictive control, in another case it is indirect field oriented control, and also the motor is subjected to same torque level. And what we see, for the same coolant profile, the MPC results 1.7% lower IGBT temperature. That means if we applied model predictive control instead of indirect field oriented control, the maximum junction temperature on average is lower than 1.8% when the inverter is subjected to indirect field oriented control. That means the control of the inverter also has a huge impact on the temperature profile of the device. So we see three classic examples. In one example, we see what is the impact of mission profile, that means the speed profile. In another one, we see what is the impact of different charging level. In one case, it is fast charging, another case, it is slow charging. And third case, we see what will be the impact of the control on the temperatures. Then this is our mission profile oriented reliability tool. We call it relate tool for our e-powers. So this tool will subjected to all these mission profiles. Then we take what is the converter specifications and the EV load profiles. Based on that, we have different types of drivetrain model, whether it is an automotive car or a long haul bus or a long haul truck. Based on the drivetrain, we get what is the voltage level, what is the power request, and what is the coolant temperature for the converter. And then based on the electrothermal model and the electromechanical model, we find out what is the stress during those mission profile in the converters. After that, we give those profile to the counting algorithms to count what is the number of failures in terms of junction temperatures and in terms of temperature swings. Based on that, the accumulated damage has been calculated. So accumulated damage is actually one number, but all these things cannot be static, like your EV will not be subjected to one profile. That is why we mix uncertainty in the model, and based on it could be uncertainty in the mission profile, it could be uncertainty in the converter parameter, it could be uncertainty in the drivetrain models. So these uncertainties has been given as a mix, and then based on that we identify what will be the behavior of Monte Carlo. That means what will be the fault in case of 100,000 of samples. So out of this, we get a probability distribution functions, which gives us that number. That means if it is it has 100,000 of samples, what will be the lifetime of the components? And then based on the components association, that means how many components in series, how many components in parallel. Based on that, we calculated the cumulative functions, and after getting the cumulative differential functions, we identify what is the system level lifetime of this DUT if this is subjected to those profiles with this number of uncertainty. We can tell what is the reliability number of the DUT. So this is the software tool which takes in account many real field data and also many simulation data in account. Then we are given some use case examples. This is the first use case where we will see what is the impact of mission profiles. So in this case, the DUT is high voltage DC converter, and we see the same two profiles that we mentioned before. One is urban, one is another one is extra-urban. And in this DC-DC converter, we consider one redundancy. That means if one leg is fault or one leg is phase failure, the high voltage DC is still carry out its functionality with less power, with less efficiency. So we see the redundancy improves the lifetime almost around 4%. And the same DUT, if it is subjected to urban, the lifetime is almost twice in comparison to extra-urban. So that means the mission profile and the redundancy has a huge impact on the lifetime of the automotive high voltage DC-DC converter. Then this is an use case result 2, where we will show the impact of the control. In that case, it is inverter which encounters the same WLTC profile, the same torque requested torque is given. We see in the MPC, the inverter losses are really low. In some case, the inverter losses goes close to 0. But in IFOC, the inverter losses are always remaining at 400 watts. That means the inverter losses reduces around 26% in case of MPC. But what we identified, it is really an interesting story. That means the IFOC resulted to almost 21% longer lifetime. Why does it happens? Because it is the temperature swing. So the highest temperature may give you better lifetime if there is lower temperature swing. So if you really see, the MPC never goes to zero. That means the temperature swing is very less in case of MPC. But when it is IFOC, sometimes the losses goes from 100 like 1 kilowatt to 0 watt. That means there will be expected a huge temperature swing in the IFOC, but in MPC there is no such aggressive swing. So that means the lifetime in case of IFOC improves in terms of MPC, which is almost 21%. So here it is another example from the high level charging strategy. So the one charging given power using the conventional charging, whether it goes from 20% of SOC to 95% of SOC, and in another case we give a smart charging current request, and in both cases we see the smart charging current request improves the lifetimes by 55%. So I come almost to the close actually. So this is the new planned reliability research infrastructure, where we have automated power cycling test bench, where we have mission profile data logger, the high precision data capturing equipment like thermal camera, D-space, power analyzer, then LCR meter. We have cloud computing Hydra PC, and finally we also receive power dynamic double pulse test analyzer. So for more information, please go through this link. You can see the details of these devices and their test capability. And this is a Flanders make, that means a Flemish funded project. And on the left hand side, we can see first test results that executed in our accelerated power cycling test bench. So what we see, we take 4 Brent independent MOSFET, and in case of MOSFET 1 and MOSFET 4, the lifetime increases almost twice in case of MOSFET 2 and 3. What is the difference between MOSFET 1, 2, 3 and 4? It is actually how the MOSFET has been added on the heatsink. So the thermal interface material is different in 4 MOSFET. In MOSFET 2 and 3, there is no thermal interface material. In MOSFET 1 and 4, there is a thermal interface material in between the switch and the heatsink, which increases the lifetime by a factor of 2. That means the thermal interface material is also important to be taken into consideration, and also it depends which type of thermal interface material you are using, whether it is phase changing material, whether it is thermal grease. So based on that, the lifetime also changes. I will not go details on this presentation actually. And for you guys, we are looking for really good PhD candidates who can join our research activities to carry out the predictive health maintenance, the accelerated lifetime test, and the modeling. Please contact our Professor Omar Higazi, or also you can contact me or Dayadong Zong. So I welcome all of you to apply at our lab for reliability research activities, where you can model digital twin, where you can carry out the accelerated lifetime test. And now this is end of my presentation. I thank you all for your patience and for giving me opportunity to give a talk over Vietnamese power electronics community. Thank you.
Thank you very much, Sajib. And yes, indeed, we also thank you to spend time. We really appreciate that you have to wake up early and then give this presentation. We really thanks. Okay, and Now we go to interactive sections, question and answer. If anyone has any questions, please put here in the chat, or you can unmute yourself and ask our presenter. I would ask if audience, if anyone has interesting questions.
Hello.
Hello.
Yeah, my name is Thang Lee from Seoul National University of Science and Technology in Korea. So I have a question about your lab is working on the reliability analysis, and then we also have several paper working on the converter level. That means switch level, like open circuit fault or short circuit fault on a switch. I have a 1 and 2 paper writing about that. But I want to ask you is, did your lab working on the like the open circuit fault analysis or short circuit fault analysis or not, or are you working on the system level?
So actually how it works, it is based on the request we received from the industry. Currently what you said, yeah, I know the there are several studies also, the short circuit faults on the SiC MOSFETs, this type of study also carried out, but we do those studies during the gate drive things, like how the gate drive could protect open circuit and the short circuit failures. Those has been taken into considerations during the design of the gate drives. So this study has been done that way, but not directly in reliability lab, like what is the impact of short circuit or the open circuit failures in the device level. That is, I didn't study this in our research lab. But the way it can be protected, that a study has been carried out during the gate driving design of by some of my colleagues actually. Like one of my colleague has been design a very advanced modular gate drive for SiC MOSFET, where he has taken all of these considerations into account for a double side cooled SiC MOSFET, like how to protect very surge current, and short circuit current is cannot be detected by hardware, but even though if there are some protections also has been provided, like using the gate triggering, he tried to do some protections over there. But yeah, again, to answer your question, so we didn't see the impact on the lifetime study yet, but maybe in future, if there is some questions coming from the industry, of course we will go through it.
Okay, thank you for your information. And I have the other question related to the calculation or model of the lifespan. So normally for analysis, we can calculate the lifespan of the device, each device. For example, we can read the data sheet in order to know the lifespan of that for the switch capacitor or the other also have. But in the converter, when you calculate the total lifespan of the one converter, that means it's not only device, right? So what is parameter did you add this estimation, or what is model inside your model?
Okay, so actually, if you see any datasheet of the device or switch, like Infineon datasheet for the switch, I never found actually the lifetime datasheet. Like what will be the lifetime. So what we do, we carry out the accelerated lifetime test of the switches and then identify the parameters, like the impact of active thermal control, impact of current, impact of different parameters, and then we design the electrothermal model based on the datasheet that is provided by OEMs like Infineon or GAN Systems or Cree, and then the lifetime model estimate if this device facing this electrothermal electrothermal repetitive cycle throughout this mission profile, what will be the lifetime? So the lifetime parameters come from accelerated lifetime test, but the electrothermal model comes from the datasheet that is provided by the OEMs. So it is actually mixed hybrid model.
Yeah. Okay, I understand. And I have one more question related to how you can test the reliability in the real.
Yeah, that is what I'm saying. Using accelerated lifetime test bench. So like you take the switches and the capacitor, and the switches will be on the same heat sink that your DUT will be attached. Then you will put the repetitive electrothermal cycle, that is called thermal cycling. And also you can change the humidity, the temperature inside the cabinet. Based on that, you can see different impacts of the thermal cycling, and also the impact of the current. And we will test until the device comes to failure. And how do we measure the failure? We measure the failure by seeing the change on RDS on. If the RDS on increase around 5% from its initial RDS on, that means the device comes to failure due to the solder fatigue. So that is how we measure the lifetime.
Yeah, okay. Because if for example you're using accelerator, you say the
accelerated lifetime test, yes.
Yeah, that related to you test the thermal, you increase thermal or increase the current or increase humidity.
Yeah.
But but how long for test one time, for example?
Okay, how long the test one time? It depends on how good your device is. In one device, we have to carry out the test for 18 days, like 18 multiplied by 24 hours. And we
18 days.
Yeah, 18 days, 24 hours. You give the thermal cycling. That means you heat it, you cool it down, you heat it, you cool it down.
Yeah.
That's why we see that the 5% increment in the RDS on, and also 2.5% increment on the VDS on. That is how we measure the lifetime, and the DUT comes into the end of its lifetime. So that is how we measure.
Yeah. Okay. Thank you for your very nice information. Yeah.
Sorry, thank you for the presentation. I just have very quick questions regarding to the parameter design. So we have something like the number of cycle, the maximum temperature, and the sweet temperature. So from your experience, which one is the most critical, may affect to the lifetime of the devices, and specifically, and also for the whole power electric system?
So for the switch, it is actually the temperature swing for sure. It is the temperature swing rather than the maximum temperature. Like if your swing is not that aggressive, but you go close to 150 degrees centigrade in case of SiC. And in another case, if your maximum temperature is 100 degrees centigrade, but you has an aggressive swing of 30 degrees centigrade, that device will die fast. That means you are operating at maximum temperature, but your swing is not aggressive. You may operate close to the ceiling of the temperature. But if your temperature swing is very aggressive, but you are below than your maximum temperature, that device will die fast.
Okay, I see.
This is for SiC MOSFET, but you cannot take it 100% correct for all device. I didn't test. So I test MOSFET, SiC MOSFET. So that is true for SiC MOSFET. The temperature swing is responsible for the failure of the SiC MOSFETs rather than maximum temperature.
Okay, thank you. I had a second question. It is also quite quick. So normally, like the lifetime of the system, like maybe 10 years or even 20 years, the actual cycle of that. So how long it's gonna be like in the lab or testing environments? You just mentioned something like 80 days, and is that like could be that short, or it could be like a few months? Otherwise, it's gonna take a lot of time for the getting the result. So
Name, it is
my
how
question is how
actually
short it could be, or it's gonna depends on specific converter.
No, it is especially how you stress the device. So the example I give, so the device was rating for 120 amps. So we always stress it like 0 amps to 120 amps for 2 seconds, and then we heat it off from 120 to 0 seconds. So you can see there is an aggressive temperature swing. So that is how it is heat up, cool down, heat up, cool down until it fails. So if you want to do it very accelerated way, you can keep like this from 0 to its maximum ratings, or even maybe you can overload it. Like if it is rating for 120, you can give 150 degrees, 150 amps, then it will die fast. So you have to test several criterion, then you can come up into a statistical model how it is degrading. So
Okay.
it is a good idea to degrade it fast. Actually, the first sample, degrade it fast, very fast. No matter how you degrade it fast to see it comes to fail, and then see where is the failure. And then the other one, you respect the norms and respect the standards, then you could have a very good idea actually what is the root cause, that you will identify very fast, that it is temperature swing. Okay, so this is some actually the idea like you can try and carry out.
Okay, I got that. Thank you very much.
Thank you for the questions, and audience, from audience side, if any other questions.
Sorry, can I have one more quick question about the? You said your lab is working on the SiC MOSFET. So but nowadays we have a more problem with the SiC MOSFET because they can switch at very high frequency compared with SiC MOSFET. So I think I mean in your lab also working on the SiC MOSFET, or you have some publication related to SiC MOSFET?
Yes.
Yeah.
We have multiple publication on SiC MOSFET actually. Yeah, some MOSFET are double side cooled MOSFET, which is really very recent come into the market, and in some MOSFET it is half bridge module. So yeah, so the recent publications we do in IEEE journal, it is regarding half bridge SiC MOSFET.
Okay, thank you. I will read your paper. Thank you.
You are welcome.